we assume that this condition is satisfied over a certain region, so there could be a delta z, that the z plus delta z can define a delta z within this region when a neighborhood exists. So you can say that the f is defined like that. So this f at the f z plus delta z would be like lz plus a delta l, right? And then you use this real and imaginary expression. So this would be u plus I v and plus delta u plus delta v. Right. So that case that is straightforward. Right. Now you can this delta f or delta u and delta v. You can just use your calculus of multivariable function to do that. So like delta u is just delta u is just whatever partial u partial x times delta x, and delta x and delta z is defined. So this delta x plus delta y. Let's look at that. Any small changes just separate the real and imaginary part. But then as a function of real x and y, so we can use the calculus that you learned. So that's partial u, partial y, and likewise delta v is partial u, partial v, partial x, partial v, partial y, delta y. Okay, now you substitute everything in here. So so f is u plus this is yeah, that's for u. Yeah. This is f, right? And but this is delta f, this is delta u. And so you can just write delta f as delta u plus I delta y. Now just substitute everything in here as partial u, partial x, delta x plus partial u, partial y, delta y plus I partial u partial v partial x plus partial v delta, yes, a delta partial v partial y, right? It changes this one. And the idea is now you can substitute the Cauchy-Riemann condition, right? So we can now try to say so your partial u partial x, you want another partial u partial x here, and partial u partial x partial v partial y. So partial v partial y can be substituted in partial u partial x. So we want this to keep this partial u partial x in here, and this also changes the partial u partial x, right? But these two are the same. So you have delta x, group delta x, and there's an I here, delta y, right? And then there's partial v partial x in here, and we can change this to minus partial u. Actually, I can change partial u partial y to minus partial v partial x, right? And then so both have a partial v partial x, and there's I also, I partial v partial x. And there's a delta x here. And this change to minus partial u. This is partial u partial y. This one change to minus partial v partial x. Take this out, and you take an extra I out, right? And there's a minus sign. And so this also changed the other one because there's a minus sign, and you take the I out, but the I times I is minus one, so that's a minus sign. Okay, so that now you have both have this delta x plus I delta y, which is exactly delta z. It's a right, so it's a partial u partial x plus I partial v partial x delta z. Right. So that dfdz now is defined as this minus f, which is delta f, and divided by delta c, limit of delta z goes to 0, and delta v, delta f divided by delta z, which in this case is this partial u partial x plus I partial v partial x. Okay, so now we finally, by the definition, is going to this two function, partial u partial x plus I partial v partial x. Both are well defined, assuming u and v are well behaved functions. And it's independent of delta z now. So now that whatever delta z, we still have the same thing. So it means that following the definition of derivative, df dt can is the same, whatever delta z, whatever direction delta z goes to z. Okay, so this is the other way around. But that requires that because we use this two condition in going from this step to this step, you require this to satisfy over the whole region. There's a larger region outside Z. We require that to satisfy over this region so that this process can go through. And then once this is satisfied, then df dz at this point is defined, well defined. So after that becomes a differentiable. So the other way around is a Cauchy Riemann condition satisfied over a neighborhood of a point. Then that point is differentiable.